What's up, everybody? Welcome back to another weekly live stream from Scalar Learning. And today is Tuesday, which means we are knocking out SAT problems straight from the source, straight from Khan Academy. And in particular, what we got today on the menu is linear and exponential growth. So let's jump into it right off the bat. Now, big news, SAT coming up a week from Saturday. So that's May 4th, SAT is coming up. A couple of announcements. We're going to be doing a long preparation session, 6 days, starting Sunday, this coming Sunday, all the way through Friday. So it's a 6-day cram session for the math section of the SAT. If you guys really want more, message me, let me know. I can try and add on something on Saturday for everybody who's prepping for that test. And just a little bit of more news, I will be taking that test as well. So I'll be prepping with you guys the entire time, and then we'll be knocking it out together on May 4th. We'll do a debrief, a score reveal, all that good stuff. All right, without further ado, let's get into it. Here we go. So we are doing this one. Now, I'm seeing this problem for the first time. As always, if you're new to the channel, I don't do these with preparation. I do them live, and I want you to see the thought process in my mind, especially even if there's a question that I'm not exactly sure how to approach, how I break it down, analyze it, and do my best. So here we go. An astronomer observes the velocity of a galaxy at a distance of this far away. To calculate its distance 2 billion years from now, velocity of a galaxy, a distance of. So it's that's a unit of distance apparently. To calculate its distance 2 billion years from now, using two different models. In the first model, the distance from the galaxy to Earth, let's say galaxy Earth. The distance from the galaxy to Earth increases 9 every billion years. In the second model, the distance from Earth increased by 10%. So it's a multiplier of 1.1, right? Every billion. Okay. 2 billion years from now, how much farther would the galaxy be in the second model compared to the first model? Okay, this is the second model. This is the first model. Okay, so 2 billion years from now. So right now it's 100. And in 2 years for option number 1, it's going to go 9 and 18. So it's going to be at 118. All right, that's straightforward enough. For this one, it's 10% every billion years. So after 1 billion years, it's at 110. This is a calculated problem, by the way. After the second year, it doesn't go up to 120. It goes up to 1.1 times 110, which I believe is 121, but let's double check. Yeah, and then move it over. So after year 2, it's 121. So basically what I'm doing is I'm multiplying it by 1.1, then multiplying the new value by 1.1 again, and we get that value of 1. Did I say 122? Oh my God. What's wrong with me? 121. I wrote the wrong thing. That's crazy. Okay, so 121. I'm even going to just be extra safe. Multiply 100 times 1.1 equals times 1.1, 121. So it's a difference of, it's a difference of 3. Boom, done. Next. At one community college, the cost per credit hour for in-state has increasing by $3 per year. In another community college has been increasing by 9% every year. This year, the cost is $65 at both colleges. To the nearest dollar, what was the positive differences in cost 2 years ago? Okay. So it's 65 for both. So the way we would do it is, $3 every year. So then what is the positive difference in cost 2 years ago? So 2 years ago, 1, 2. The first one's easy. It goes back 62 and then 59. There's a couple of ways we could do the second one. I could set up an exponential equation and say, hey, it's increasing by 9% every year. So this is the 9% increase to the t years, whatever, times some initial value. And we could sort of solve for whatever our initial value is maybe at 2 years ago, right? We could say 65 equals this value x when t equals 2, because this value right here is 2 years from that point. And then I could solve for x. Actually, I guess that's not a bad way to do it now that I set it up. I was going to do something different. I'll do it 2 ways, okay? So I'll show you both ways. So first is 1.09 squared, and then what was it? We divide 65 by that, right? My second answer equals 54.7, so 55 if we round up to the nearest dollar. So it's a difference of 4. Let me just put that in red over here so we know our answer is $4 here. And then I'm going to show you the other way that I was going to do it, which you don't even have to know this formula, right? We don't have to know the formula for exponential growth. Okay. So we can go step by step. The year prior, we can say that 65 is 9% greater, 1.09 times whatever we had the year before to get 65. So first we divide 65 by 1.09. And we get that, whatever that is, 59.63. 0.63. And then to get back here, we say 1.09 times the year previous, I'll just call it y, equals 59.63. So again, to solve for y, I'm dividing 59.63 times 1.09, or whatever this answer is, divided by 1.09. And we get the same thing that we got before, 54.7 roughly. I think maybe it was a little, was it the exact? I think it was the exact same. It should be 54.7. So we'll round it up to, let's just say 54.7. But we could round it up to 55. And again, that's a difference of 4. Let's just do double check, make sure we got the exact same thing. 1.09 squared. And then I said 65 divided by second answer. Yeah, it's the exact same. So there we go. So to the nearest dollar, the positive difference was 4. All right. Next. A pilot is testing the change in external pressure during... I think these problems, by the way, let me just go on record saying I think these problems are very difficult, not because of the calculations involved, but because of the amount of words. To be honest, even I get a little anxious when I see a paragraph like that. I love it when it jumps straight into the math, and that's when I get excited, is a problem that's just straight numbers. But these ones, you have to parse the information. But just remember, they're actually usually on the simpler side once you get through all the extra stuff, put it that way. A pilot is testing the change in external pressure during ascent from a pressure of 1 atmosphere. Okay. If the plane ascends at a constant rate, the pressure drops by 30% every 10 minutes. If the plane ascends, the plane ascends at a constant rate. The plane ascends at a decreasing rate. The pressure drops by 0.1 atmospheres every 10 minutes, right? Same type of problem. After 30 minutes, what is the pressure at a constant rate of ascent? Constant rate, that's this one. No, sorry. Constant rate's up top. This is constant. What is the pressure at a constant rate of ascent? So it's this guy minus the pressure at a decreasing rate of ascent, minus that, after 30 minutes. So we're starting at 1 atmosphere. Okay. I may want to use an equation here because, 30 minutes. That's not bad because this is in 10-minute increments. So here we're starting at 1. After 10 minutes, let's go 20 minutes, and let's go 30 minutes. After 10 minutes, it's dropped by 30%, so we're at 0.7. Okay? After 20 minutes, now you can multiply by 0.3 and subtract, or I can just keep multiplying by 0.7. If we're losing 30%, it's just going to be 70% of whatever's here. So I can multiply 0.7 times 0.7, which is 0.49, and then multiply this again by 0.7, which I'll use my calculator, 0.4, it's calculator, times 0.7 equals 0.343. Okay. And then the other one, this is the other guy. We're starting at 1, then we drop by just 0.1 each time. So 0.9, 0.8, 0.7. It's pretty simple, right? So we say, what is the pressure at a constant rate, which is the top one minus that guy. So 0.343 minus 0.7. Minus 0.7. Negative 0.357, this guy. Okay, question 4. So far, so good. A single processor takes 20 milliseconds to prepare data entries and 0.1 what? Oh, 0.1 n, it's a variable, milliseconds to copy the entries. Prepare blank. Where n is the number of entries. Got it. A multiprocessor, so this is 20 milliseconds plus 0.1 n. A multiprocessor takes 70 milliseconds to prepare and copy one data entry. And whenever the number of entries is doubled, increases by 5. Hold on. How does that work? So a multiprocessor takes 70 milliseconds to prepare and copy one data entry. And whenever the number of entries is doubled, the amount of time to prepare and copy them increases by 5 milliseconds. Hold on. So what is that? 5. How do I represent that? Okay, I'm not sure how to represent that in a formula. Given 120 milliseconds to prepare and copy data entries, which processor type can prepare and copy more entries? And how many more entries can it prepare and copy? I got to be careful because this formula up top, I definitely know that's fine and that's pretty easy. So it's 120 milliseconds. This is the total milliseconds that it takes, right? And we're solving for n. Subtract 20, subtract 20. I have 0.1 n equals 100. Divide by 0.1, divide by 0.1, n equals 1,000. So the single can do 1,000. Okay, I'm gonna have. I think I can do this without a formula. Let me see. So 70 milliseconds, and whenever the number of entries is doubled, the amount of time, 70 milliseconds to prepare and copy, increased by 5 milliseconds. Okay, given 120, let me think about this. So we're starting at 1. So that's at a single one. So that's at 70. And 75, we'd have 2. 80, we'd have 4. Right? I'm adding 5 milliseconds every time. So when I add 5 milliseconds, now I can do 2. I can double it. Now I can do another 5. I can double it. Now I can do another 5. I can double it. Another 5. I think I see now how I could have come up with an equation. But this is going to work. 95, 32, 100, 64, and then 4 more times. 105, 128, 110, 256, 115, 512, and then 120 is 1,024. There we go. So you can see the difference. The multi can do 1,024. The single can only do 1,000. So it's 24 more entries, and that's it. Hope I understood that right. Definitely, I knew the multiprocessor would do more. Wait, why is there such a big difference in numbers? It's so weird. Okay, let's just see if it's right. Yeah, it's right. I don't know. These ones threw me off because they're all so big, and then this one's tiny, but it's all good. Let's see the equation they used. I'm curious for the exponential. Oh, yeah, they just did this, and then they took it to the 10th power, right? So that's what I was thinking after the fact. I'm like, how many times does it go up from 70 to 120? And there it is. 5 goes up, it goes up increments of 5 10 times because it's 50. And that's great. Okay, next and last question for today. A surveyor discovers that the total combined lengths of all roads in miles of a particular city was 500 at the beginning of 1950 and increased 125 every 10 years. So plus 125 every 10 years. Additionally, the number of cars driven in the city was 50,000 and increased by 20%. Right, hold on. Let's do 500. So this is the starting point, up 20. Increased 20% every 10 years. What was the difference between the number of cars driven in the city per mile of road at the beginning? Oh, wow. Okay. Got it. So cars driven per mile, which means number of cars divided by miles. So in 1950, which is here, it's the number of cars divided by that, which is just 100. So 1950, 100 cars per mile. Okay, and then in 1990, let's see what happens. So this one goes up, so it's 60, 70, 80, 90. So it goes up 4 times. So here it's 625, 750, 875, 1,000. So 1990, the number of cars, not number of cars. Excuse me, the miles is 1,000. And let's see the number of cars. So it's going to increase every 20%. So let's put cars in red right below it. So it's 50,000, of course, in 1950. Then it goes up by 20%. Now it's at 60,000. Then 20% of that is 12,000. So now it's at 72,000. Then that's 14,400, 86,400. Don't do this in your head if you can avoid it. I'm just being lazy a little bit. This one I'm going to not do in my head. 86,400. 1.2 equals 103,000. Okay. So now I'm going to divide this by this, right? The number of cars divided by the available miles divided by 1,000 equals 103.68. So it's gone up a little bit. So there's the difference. It's gone up by 3.68. And that's it. Yeah. I don't see anything else. What was the difference? Yeah. Reading it correctly. Boom. Done. Okay. Let's see if there's any questions quickly. Oops. What's up, guys? Can you please tell me how you know what to do once you see the question on the SAT? My go-to is, okay, so part of this I'd have to say is experience. I've practiced and I've done so many practice problems that I somewhat instinctively know what to do in a sense in terms of setting up an equation or writing stuff out. But I'm trying to help you see my process, and my process is pretty simple. I just start writing stuff down so I can organize it in my mind. I'm plotting out things so I can make sense of the numbers and more importantly, the relationship of the numbers and the variables. So that's my ultimate tip is just start writing stuff in terms of organization. If you just keep it all up in your head, that problem would have been very confusing for me if I didn't write anything down. I wouldn't have been able to parse it. So write it, organize it, and you don't have to do it the way that I did it, but that's the way that I'm comfortable with, and that's how I approach and problem solve, okay? So guys, good luck for everybody. If you like this video, if you're watching now, please click the like button. It really helps out the channel tremendously. And leave a comment if you have additional questions. So Rubni, I know you just asked me a question. If you have more questions, especially specific ones, that's very helpful. If there's specific problems you want me to do and solve live, I'm happy to do it. Thank you guys so much. Get ready for a big prep week next week to get you guys ready for the SAT on May 4th. We're going to do it. And I wish you all the best of luck. Take it easy.